Good afternoon, good morning, good evening, good night. So thank you all that are here today for a new IEEE CASS Rio Grande do Sul Talk 2021. As you can see now, today we have Professor Pierre-Emmanuel Gaillardon from University of Utah in USA. So thank you very much, Pierre-Emmanuel, for accepting our invitation and to talk today about this very interesting subject. We have also here Professor Fernando Moraes from the Catholic University of Rio Grande do Sul at Porto Alegre, that will be the session chair today. But before giving the floor to Fernando to introduce Pierre-Emmanuel, just some announcements of next events. So next week, we are not going to have a CASS talk because in reality we have several invited talks next week in the IEEE CASS Seasonal School on Circuits and Systems for IoT, the 3rd edition, that will be next week in Bordeaux. As you can see, it will be in hybrid mode. And then for the virtual attendees, the registration is free. So it's something very special, this opportunity. So the school will run from Monday to Friday. And if you go to the web page, you can do your registration still today. And you can see the full program with a nice set of talks covering different aspects of IoT, from circuits, systems, analog stuff, devices, to machine learning, deep learning, and so on. So I think the program is a very nice one. Don't miss this opportunity to attend the seasonal school on circuits and systems for IoT. And the week after also, we have another event that is the 11th edition of the IEEE CASS Rio Grande do Sul workshop, together with the 3rd Young Professionals workshop. So you can address the web page to see the full program, but you can see here a set of invited speakers. So we have invited speakers from many locations from the world. So with very nice topics that will be covered. So don't miss this opportunity. So it will be from Wednesday to Friday. So 3 days of workshop. So it's a nice opportunity, and the registration is also free. So it's also another opportunity to attend very nice talks without any cost for you. So it's open for people from all around the world. Then also, I remind you, if you are not aware yet, the 4th edition of the IEEE IBM so Circuits and Systems Society, Electron Device Society, AI Compute Symposium, that is being organized in cooperation between the societies and IBM. So 13th, 14th, so October, 2 days, and the registration is free. So you just need to address the website of the event to do your registration now. Also, the week of October 18 to October 22, generated from Montpellier in France, there is the Nano Connected 2021. So it's a conference about nanotechnology. And if you see the extract of the program here on the right, you can see that each day there is 2 main fields that are selected. For example, Monday is food science and electronics. On Tuesday is materials. Wednesday is water science and mechanics. Thursday, there is an international week at Polytechnic that is also presented. And Friday, medicals and the near field optics. So the students are recommended to attend the workshop. That is just 1 hour each day. And then there is 2 invited seminars per day. So it's also a nice opportunity. So it's being organized by the Center for Nanotechnology of the Federal University of Rio Grande do Sul, Brazil, the Polytechnic Montpellier in France, the Universidade Yachai in Ecuador, and the Universidade Simón Bolívar in Venezuela. So the registration are free, and they are open till next Monday, September 20. So I recommend you to do your registration just after the talk of Pierre-Emmanuel. Then also another call here for the 5th edition of the IEEE Seasonal School on digital processing of visual signals and application. And the call for posters deadline is extended to September 20, so next Monday. And if you address the web page, you can see the full program. That is also a nice one. And there is also some nice awards for the best posters. And October 8th, we restart again the CASS talk with Professor Davi Atienza from EPFL in Switzerland, talking about brain-inspired edge AI architectures. Then the week after, we have Professor Nader Bagherzadeh from University of California at Irvine, talking about some aspects of machine learning computer architecture. October 22 is time of Professors Enrico Macci and Gianvito Borghesi from Politecnico di Torino in Italy, talking about the role of ICT in the Industry 4.0 paradigm and the neuromorphic technology opportunity. October 29 is time of Professor José Zambuja from Federal University of Rio Grande do Sul in Brazil, talking about the network computing and switch virtualization walk into a bar. Oops. Sorry. And November 5th is Professor Luca Benini from ETHZ in Switzerland and Università di Bologna in Italy, talking about an open platform approach to low-power computing system design. Soon also we are going to announce the other talks scheduled for November this year. Then if you lost the talks that were done last year and also the ones that were done this year, as well a large set of industrial talks and many other talks in other events organized by the chapter Rio Grande do Sul, you have just to search in the playlists of the YouTube channel and to see the full set of talks, you have to scroll in the YouTube to search for the full playlist. Then also the LASCAS 2022, so the CASS flagship conference in Region 9, that means the CASS International Flagship Conference organized each year in Region 9. The final call for paper deadline is September 26, so you still have 9 days to prepare your papers. And as you should know now, there is a selection of best papers that are published in a IEEE Transaction Sequencing System 2, and the ones that are selected for TCAS 2, they will appear in a journal by the moment of the conference. So it's a fast track to have a good paper in a good journal, and also considering the presentations, questions, and answers during the conference, there is another set of best papers that are selected to prepare extended versions for IEEE Transactional Sequencing System 1. So there is a special issue dedicated to the CASS flagship conference. So the deadline, as you can see, extends to September 26. So we still have 9 days to prepare your papers. So the conference is scheduled to be face-to-face one, but for the ones that have any problems about traveling to Chile, it will be organized in an hybrid mode. So don't worry that you can also present your paper by video conference. And also be prepared for LASCAS 2023 in Ecuador and LASCAS 2024 in Punta del Este, Uruguay. And also together with LASCAS 2022, we have the 28th edition of the Iberchip workshop, where you can have your papers not only in English, but also in Portuguese or Spanish. So this is another option to submit your papers. And also the primary A, that will be the 5th edition of the conference dedicated for PhD research in microelectronics. So, Also, encourage all the people in universities around the world, and many here also in Region 9, to prepare your teams to participate in the student design competition 2021-2022. The registration is open, and the competition has 3 phases. The first one at chapter level, the second one is regional level, and the winners of the regional level, 3 members of the team have all the cost of traveling to Austin, that is the location of ISCAS 2022, to participate in the final competition that we hope that we'll be able to do face-to-face. If no, it will be by remote mode, but I hope that next year it will be possible to be face-to-face. And then also there is a nice award for the winners. I think it's $3,000 for the team that will be the winner. So don't lose this opportunity, and start working as soon as possible. But today we are here for the talk of Professor Pierre-Emmanuel Gaillardon, talking about under the hood of OpenFPGA. And then I now give the word to Professor Fernando Moraes from the Catholic University of Rio Grande do Sul at Porto Alegre to do the presentation of Pierre-Emmanuel Gaillardon. Thank you.
Thank you, Ricardo. Welcome, Pierre-Emmanuel. So Pierre-Emmanuel Gaillardon is a associate professor in Electrical and Computer Engineering Department of the University of Utah, Salt Lake City. He holds a PhD degree in Electrical Engineering from CLT Grenoble, France, and the University of Lyon, France. Prior to joining the University of Utah, he was a research associate at the Swiss Federal Institute of Technology, EPFL. Professor Gaillardon received several awards from NSF, IEEE, DARPA, and ACM. He is a senior member of the IEEE. Welcome, Pierre-Emmanuel.
Thank you very much. Thank you very much for the kind introduction and the great invitation to present the work my lab has been doing around the OpenFPGA framework. I believe the slides are not live yet. Excellent, thank you. So today I'm going to talk about the OpenFPGA framework with a talk entitled Under the Hood of OpenFPGA. So first of all, let me start by asking the question of why OpenFPGA. Well, I'm not going to explain again what FPGAs are, but FPGAs are essential to a modern high-performance computing system. Not only they are found in many industrial, defense, IoT application, but they're also ubiquitous in wired and wireless communication, audio-video broadcasting, data centers, and so on and so forth. However, there is more and more demand for domain-specific application that would get some use or good use of any specific types of computing resources of FPGAs. I like to give the example of AI applications, right, where AI is typically DSP hungry. However, commercial FPGAs are tailored for being general purpose and may not fully capture, fully able to perform at their best in some, specific domains. So this is so basically there's a need to having the ability to create new FPGA fabrics in a very agile way. However, this is an extremely cumbersome process. To give you an illustration, from whatever requirements one might have, you need typically a large team of senior architects, people with deep, domain knowledge about FPGA architectures, to come up with new fabrics, and then having an army of hardware and software engineers executing towards those specifications to end up with a year-long process in providing you with the complete production-ready layout as well as all the supporting CAD tools. Well, here the prospect is different. and we want to be extremely transformative. What we want to do is to enable a single person, an architect, with a clever idea, with the help of our framework, to be able to create complete production-ready GDS, so ready for tape-out, and the supporting CAD tool in less than a day. It's a bold statement. There's a lot of things to be done there, but we already have been able to achieve a certain impressive milestones. In particular, we're able to have complete FPGA and eFPGA generations. We demonstrated that with 4 tape-outs in 2020. We're at 3 tape-outs this year already with a reduced team of students. We also are capable of supporting modern architectures that are fully customizable. We support more than 100+ architectures in our test infrastructure, ranging from small FPGAs like Lattice Ice40 all the way up to more complex fabric like 7 Series Xilinx FPGAs. We have a lot of strong optimization for fast physical design, which is the key of the platform here. We're designing, mid-range fabrics, 150K to 100K LUTs only requires 24 hours. So this is one of the key prospects of OpenFPGA. Now I'd like to dig into some more details and try to understand what is actually OpenFPGA. So OpenFPGA is a complete framework that, on the one hand, provides chip designing capabilities. That's what we call the FPGA prototyping flow. It's not only prototyping, can be production as well, but that's all the chip design, fabricating, manufacturing an FPGA. And for that, our OpenFPGA engine uses some high-level description languages, bind to standard cells and custom cell libraries, and is capable of spitting out netlists that goes to place and route, as well as complete test bench strategies for pre-silicon sign-off. But in addition to that, we also have the complete end-user flow that is supported, because once you have an FPGA, you need to be able to implement a circuit on it and generate the configuration bitstream for that to be useful for your end user. So this is also fully supported on the FPGA end user side. Now, however, what I represented right here is typically what people would do to support FPGA. This is resembling the SIMB flow infrastructure that is architected around the VTR framework from the University of Toronto, and is capable of generating bit streams to many different fabrics. What we try to do is that instead of having a clear separation between the two, we're in fact working on a single code base. This is one of the key elements of the OpenFPGA technology. As I said before, FPGAs are typically designed where you have a hardware team and a software team. What we're trying to do is to scratch this model and only have a software-oriented approach. So what we do, in fact, is that we have a core infrastructure that is derived from the exploration and end-user support ecosystem, with in particular the tool Yosis from Yosis HQ and Claire Wolf, as well as the VPR framework from the University of Toronto and Von Betz maintaining that. These two core technologies are extremely popular to do FPGA exploration. What we do is that we enhanced that architecture by providing the ability to generate from that core duo complete Verilog representations of FPGA fabrics that can then be fed into a floor planning, feed-through generation, physical design enhancements, basically to implement the structure. We also enhance that by generating design constraints for implementing powerful and high-performance fabrics, test bench generators for verification, as well as the FPGA bitstream for the FPGA programming. So as you can see, we do not have at all two separate tools. In fact, it's a single code base that provides you the chip design flow capabilities alongside with the end user design flow. And that is a very powerful paradigm because it helps us generating architectures that can only be supported by the software. You never end up in a situation where there are clever ideas from the hardware that are very difficult to handle from a software perspective. So that's really the crux here in supporting all of that in a unified platform. Now, I just mentioned that we are using architecture descriptions, but how customizable can our architecture be? Well, here's a typical, very broad overview of what we can have, of what we do, as a matter of fact. So we use a high-level description language that is XML-based. We took inspiration from the language designed and used by VPR for architecture exploration, and we enhanced that to provide additional instructions to our system to know how the fabric should be implemented. Let me give you some examples there. This is the representation of an heterogeneous FPGA fabric that you have right here. Inside of the FPGA fabric, you have tiles with switch blocks, connection blocks, configurable logic blocks, within which you do end up with, fairly complex fracturable structures eventually with multiple 4-input LUTs and whatnot. So what happens here is that our language helps you define what blocks you have in the different elements. So for example, here we do instruct the tool to use a flip-flop that is a high-speed flip-flop.v that binds to a given standard cell library or some custom cells. In addition to that, we also have capabilities for the tool to auto-generate architectures. If I dig into just this basic logic element to give you a stronger understanding of what I mean, well, we do have some constructs that help you tell the tool what you are expecting to have. And the tool will be auto-generating the end result or the end architecture you're looking for. So for example, right here, we say we have a multiplexer. Okay, this is great, but we want this multiplexer to use a one-level structure, and we want this one-level structure to have some input buffers implemented using some inverter X1s and no output buffers, for example. Therefore, your OpenFPGA infrastructure will generate the proper netlist using the proper set of cells that will implement this type of architecture. So it's somehow intent-driven. You express what your intention is for your various blocks, and the tool auto-generates what needs to be implemented there. On the other end, you can also provide complete user-defined blocks. For example, this is a flip-flop that helps you bind to an element that you have crafted yourself, whether it is a custom cell or whether it is a bigger block, such as a DSP element, for instance. The strategy of using these descriptions is to be able to generate what I call post-tech map netlists. We know how to implement an FPGA fabric. We instruct the tool how we want our structure to be. The tool simply automates this process. We do not let the tool go completely independent and synthesize the architecture for you, because you want to control what the structure is going to be. Okay, now modern FPGAs are actually more complicated than just having an LUT. They usually implement what is called multi-mode CLBs. So you have a given structure, but depending on how you use that structure, it could be implemented as a 6-input LUT, multiple 4-input LUTs, multiple 5-input LUTs, shift registers, you name it. So what we had to come up with is a notion of physical implementation or physical views, which represents the complete implementation of our blocks. That is used, of course, for fabric generation. But then we also are capable to provide operating modes that are subsets of those physical views that are used to instruct the end user tool how to properly bind a given primitive to the physical block. In other words, if you find a netlist that contains a 6-input LUT, how should you use that block? Or if you have a netlist that contains multiple 4-input LUTs, how should you use that block? Well, so now from there, you'll get the idea. These operating modes are virtual views, virtually reduced views of the CLBs with existing binding between the physical view and the operating mode view. So we have that for arithmetic modes, we have that for independent LUT modes, and so on and so forth, depending on the modes of operation you have in your elements. So now going back to the initial view, just still representing chip designer and FPGA user to simplify the thing, even though you fully understood that we are based on the same code base. This framework is actually compatible with many of the existing tools you have for chip design verification and so on and so forth. Indeed, what we do is that the OpenFPGA generates Verilog netlists, place and route scripts, design constraints, and it is designed to interface gracefully with existing ASIC design tools, such as Synopsys ICC2, Cadence Innovus, or OpenRoad, if you want to go completely open source. We do support the 3 backends already. We have tape-out chips with these 3 backends, and keep improving and maintaining compatibility with all of that. On the sign-off front, we do have multiple also supports for HDL simulator as well as formal tools, both from the open source and the closed source front. And then last but not least, I'd like to mention what technologies have been validated with the approach. So we have validated ASAP7, GF12, 130, TSMC 40, 180, Skywater 130. That is an open source PDK, but we also validated a few more recently, UMC22, TSMC22, and so on and so forth. So that's also one of the key aspects of the OpenFPGA framework, is that it is very graceful and easy to move from a process and a tech node to another one. It requires a little bit of effort, obviously, but it's not at all comparable to what had to be done in the past with complete redesign of the IPs. So this framework basically makes FPGA fabric design a similar type of effort than designing an ASIC. And that's the gist of it. So now, of course, even though I made this claim that we can design FPGAs like ASICs, well, there are many differences when it goes to physical design. If you want to have high-performance fabrics, you need to come up with specific technologies. And let me show you what we had to implement in our system. So FPGAs are usually extremely regular. They're using an island-style architecture. So I'm just representing here an homogeneous FPGA architecture for which you only have the same block, the same tiles containing your logic blocks and switch boxes and stuff that are replicated. This can easily be extended to heterogeneous architecture with BRAMs, DSPs. Our methodology supports all of that. It's just to simplify the process here. But as you can see, we do have the same blocks repeated over and over. So how do we handle that? Well, we handle that through a hierarchical design flow. It is not novel. Multi-level hierarchical flows are well supported in modern EDA tools, right? For which you basically look at the top level, you do your design planning phase, you identify what are the key elements you want to design, you have your floor planning, design shaping, and so on and so forth that instruct the tool where the pins should align and that kind of things. And then you move to individual modules PNR, you stitch them together, and you do the top level PNR. This is typical for modern ASIC tooling. However, there is a problem along that road. The problem is that the standard hierarchical flow does not work great for FPGAs. The main reason is that in an FPGA, you end up very quickly, if you go back to my representation, right, showing you the tiles, you end up very quickly with a lot of individual modules you have to handle. So you have a number of you have a module explosion happening here. And in addition to that, you also have very stringent channel routes, especially for your top level clock. So if you look at this plot right here, this is a runtime that we got using a standard hierarchical flow, and you can see that, well, things work pretty good when you make toy examples, but it doesn't scale well. You know, moving from 40 LUTs to 2000 LUTs, 2000 LUTs is ridiculously small, right? But it already takes a much longer time, and it's an exponential growth, essentially. So while it is fast for prototyping, it does not scale well to any of the large fabrics. So we have to address some of those runtime bottlenecks and understand what can be done. The main runtime bottlenecks happen here and there. At the design planning phase, the number of instances increases quadratically with the FPGA grid size, right? moving from a 2x2 to a 16x16 fabric, boom, you just increase quadratically the number of elements you have to deal with. So boundary analysis and pin placement creates large concerns. At the top level, stitching things, ensuring clock tree is going to all the modules gracefully and being improved is also creating a major hurdle. So how did we address this challenge? We address this challenge by pre-planning and using the symmetries of FPGAs. The first thing we do is that we moved away from a notion where we have top-level PNR. This is key. So if you look at this figure, you can see that, well, if you have a 2x2 fabric, we identified with different colors what are the unique modules. And you see that, in fact, if you look at the tile structure that is using the connection boxes as well as the switch box, that tile just repeats no matter where you go in your fabric. So technically, what you want to do is to get, you want to make a complete design flow with the smallest possible fabric that uses all the individual modules, and then you want to scale things up with a top-level Lego assembly. Really top-level Lego assembly where all the blocks very nicely and gracefully abuse one to the other, so you can skip most of the top-level PNR hurdles. So that's what we do. So we try to look at what are the smallest FPGA sizes containing all the modules that can be reused for bigger designs and move from there. In order to allow that, to allow this graceful planning, we need to consider power grid. So we need to create a highly regular power grid that will make sure that every time you move from one block to another, you repeat exactly the same pattern. So it needs to be highly repeatable across the height and width of the fabric on both sides. So the power planning is very different. Power planning needs to be accounted not only because of your power expectations, but also because of the capabilities of your technology, your design kits, to know what is the spacing you need to respect between your various top-level power grid distribution and so on and so forth. So power grid needs to be adjusted in such a regular and graceful way. You also need to start thinking about global signals. Well, while these two blocks are indeed identical, these blocks receive the same signal, the same reset or clock, or load, programming clocks, whatever that is, right? So if you look about what you have a couple of top-level signals that need to be distributed to multiple blocks, either to all the logic blocks or to all the individual blocks. And in order to support that, you have to account for it at the pre-planning phase with the notion of feed-through ports. Feed-through ports are actually designed such that if you look at what you have right here in this connection box in the Y direction, you have some signals coming in, doing some stuff inside of the block, and coming out of the block to feed the next one. So you need to consider those feed through, with inputs from the west going to the various other sides of the block. So once you abute things, everything will be able to be propagated nicely through your infrastructure. So we have to do this pre-routing of the global signals. We also have to do very advanced pre-planning as well as precising of the clock routing. So if you look at the clock, there are a few complexities, right? So having a clock is no easy job, right? You need to handle the, of course, H3, getting good latency and skew. And so that requires having multiple levels of planning. So this is level 2, going to level 1, level 0, right? So you need to look at hierarchies and what metals are going to be used for your different levels. All of that happens with custom methodologies we developed for the OpenFPGA framework that is outside of any of the physical design tools that typically exist. So the trick with clock is that because of the latency and skew requirements, you need to think now of not only feed-throughs, but buffered feed-throughs, because the signals are critical. So you need to be able to handle properly some of the you basically need to be able to handle properly all your logical effort requirements between the blocks and what it feeds through. So now, bundling all of those techniques, you can see a major runtime improvement and scalability capabilities of the complete infrastructure. So now this is, again, the same plot I showed you before, but now with increased size complexities. And what you can see is that, so first of all, the top-level assembly allowed to completely cut the time required for for the pin assignments and feed-through generations. There's still, of course, a little bit of time increase linked with the size of netlists. But then, everything boils down to final sign-off, verification at the top level, and so on and so forth. So if you look at what we have, it means that you have a complete system capable of 164 K LUTs in less than 24 hours. It's been improved since then even further. Things do scale extremely well with fabrics, with 200K and plus LUTs, so modern FPGA fabrics. It's an illustration right there of an actual complete layout of a 120 by 128 fabric, 164K layout. And you can see it's very, very tiny, but you see the tile that is just one of those super small elements right here. I do not have that in this slide, but this approach also enabled us to have very scalable latency and skew and make sure that clock distributions are proper even for large fabric sizes. So now it's not only enough to have pre-planning and design, pre-planning and design shaping. What you need to do is to properly constrain your working flow, either constraining your place and route tools, or also finding methodology and constraints for performing static timing analysis to your system. So a key element also of OpenFPGA, in addition to this Verilog generation and TCL and methodology generation, is the SDC generation, so design constraint for physical design and benchmarking. So what happens here? Well, a quick illustration of, again, a CLB. Well, when you give your backend tool the block that you want to be designed, you need to properly provide all the various timing arc constraints so your tool can perform at implementing the desired performance. So that works okay. Then one can move to the full fabric, right, using the methodology I just showed you. But from there, how do you evaluate the performance of your system? That is one of the highest complexities of FPGAs. FPGAs are full of combinational loops, right? You can implement whatever you want. You're never going to implement a design with combinational loop at the end, but if you give your unprogrammed fabric, all those loops may exist. How do you instruct ASIC tools that hate combinational loops to perform properly? We do that through, again, constraints. So from the fabric, you can get your full reports, PEF, and so on and so forth. And we want to perform architecture timing analysis. So what we do is that we provide a first set of timing constraints that will only help us study some of the timing arcs without generating combinational loops in the system. So you basically generate a bunch of false path requirements. So you just extract only timings from point A to point B with the timing arc you're looking for. So you can do that across your fabric, get statistics statistics of the performance in the system, and so on and so forth. But now, in addition to know what your silicon would look like, how much performance can we get on the fabric? You can do a bunch of simulation, but what you can also do is use static timing analysis by implementing benchmarks on the fabric, getting the bit stream, and generating an SDC file that contains all the various timing arcs from the fabric. And that way you can also extract what the performance is going to be from a snake distribution inside of your fabric and telling you, this is the level of performance I get for a convolution 2D, for a RISC-V processor, and so on and so forth. All right. Now, the best achievement so far. OpenFPGA is silicon proven. We taped out 4 chips last year. The first one I want to highlight is a Frog test chip, which is a 12 nanometer global foundry test chip, relatively small in terms of fabric size, but fully instrumented and implementing modern logic element architecture, resembling 7 series Xilinx FPGAs. This chip was received, packaged on BGA substrates, tested, and is functional. In addition to that, we taped out a few eFPGA or FPGA SoCs. We did that through the Google and eFabless program that are the origin of Team Ansel from Google, who kindly invited us to participate. In the in this program, we have taped out 3 types of architecture with 3 different variations. They are including an FPGA fabric alongside with a RISC-V processor with different complexities and different blocks. What is quite remarkable here is that this 12 nanometer tape out was our first test chip that we did. It was about a 2.5 person months type of effort, while the SOFA architectures represented a 1 person months effort. 3 chips with 3 engineers over a month-ish was required to implement the complete system, design, sign off, tape out. Last but not least, I'd like to provide a quick note about the end-to-end EDA support. As I told you guys, we are using, we're based around the VPR toolchain. So that means we have complete open source Verilog to Bitstream support for our end users. In addition to just supporting that, I'd like to point out one of the sisters projects of OpenFPGA currently running in my lab, LS Oracle, which is a no human in the loop logic synthesizer. We all know how complicated it is to generate good quality RTL, right? And we all know how FPGA designers tend to sometimes cut corners when it goes to timing constraints and quality of RTL implementation. LS Oracle is a framework that enables no human in the loop interaction. Put your RTL in, LS Oracle does the job for you in giving you the best system. So it is using, of course, a few design constraints, unified synthesis scripts, and AI and machine learning to provide you with the best possible outcome. So this end-to-end EDA support is natively built into the system, and you do not need to bother about creating your own EDA toolchain. It is there for all the fabrics generated by OpenFPGA. And from here, this is also supported by community. So there is a very large support and general community living around all of these efforts. All right. Now from there, I'd like to highlight just a few pickled recent feature enhancement inside of the FPGA, inside of the OpenFPGA infrastructure, so you get also a better gist of what we have been up to in the past few months. So first of all, there has been complete code reconstructions. The engines are written in C++20. We have a shell-like interface resembling in some ways Tcl interface. We're going to keep working on that to make full Tcl support as well as Python APIs. But everything makes things in a fairly uniform way using the VPR8 engine and all the architecture support that goes with that. Fairly large build compatibilities, but more importantly, we're really using, even though it's open source hardware, we're really using the software methodologies with continuous integration, 100+ regression tests. Every time there is a bug, we add a new regression test, so we're sure that we can, keep producing a high quality environment. What is most notable is recent performance increased. Things got reconstructed to improve, to enable better runtime, lower peak memories to support, mid-range FPGA class with a high quality, small runtime and small peak memories. So this is going well. There's still, of course, further improvement that could be added, but it is already in a very good shape. I'd like to talk about the shell. So traditionally, OpenFPGA and VPR7 were shell-based. So you have a very large, command line to launch the tool, which makes things hard to follow. We have moved things scalable to a shell structure that can be either interactive, as people do for Synopsys, Cadence, whatever, when you launch your tool in an interactive command mode line. But we also have a script mode where you can just create and script your various operations, making things easy to debug and to customize the flow functionality. I essentially talked about homogeneous fabrics, but we do support completely heterogeneous fabrics as well. With CLB, memory elements, as well as different I/O capacities. This is very helpful for eFPGAs, for example, where you can have one side containing a bunch of I/Os and other sides without any I/Os, for example. Or so you can modulate things between internal I/Os and external I/Os, all that kind of stuff. We'll support multi-column heterogeneous blocks, right? So you can very easily implement inside of your fabric, even if you fancy a complete RISC-V processor. So you can, look at design shaping your structure inside of OpenFPGA the way you see fit. And you can also create high-performance interfaces on the side of your fabric. This is an example with an AIB interface, chiplet interface, that is this open source standard from Intel and maintained by the Chips Alliance. So you can easily create also eFPGA chiplets using the OpenFPGA infrastructure. One aspect that is usually overlooked when you look at traditional FPGA infrastructure is configuration protocol. Programming your FPGA is obviously fundamental, and it's one of the key aspects in addition to physical design techniques I mentioned. We do support 4 different configuration peripherals that are providing different trade-offs and in configuration time, physical design, and PPA. We have the following 4. Standalone basically means that we give access to every single configuration point inside of the FPGA, mostly useful for testing. Configuration chain is what is typically used in low-cost and small-size eFPGAs, where you have a snake-like scan chain going through your circuit to program all your configuration chains. We also have a memory bank organization, word line, bit line, to access all your configuration bits. This is very useful in eFPGAs and FPGAs based on emerging technologies, flash-based, ReRAM-based, that kind of things. And finally, we have what we call the frame-based, which is used in large-size FPGAs. It is basically distributed memory bank decoder style types of architecture, enabling partial reconfiguration and faster multi-head configurations. I will go fairly quick on the next 2 elements in order not to bother you too much, but OpenFPGA supports multi-clocks. So you can have multi-clock trees, multi-clock domains, programmable, local programmable clock network, and so on and so forth. So you can, make really modern architecture on that front as well to switch from domains to domains. Design for test is one of the fundamental elements if you want to have not only the ability to evaluate a test chip that you make, but also guarantee that this chip can be fully productized. So we support memory element with scan capabilities, so you can easily, load test vectors, read back test vectors, that kind of things. And we do that across the fabric, which enables the stability of all the flip-flops. It's implemented in our FPGAs, and it makes things also compatible with automated test methodologies, right? So you can create, ATPG test vectors for your different elements and so on and so forth. This is very non-traditional for the FPGA world that typically would craft custom bit streams to test the various functionalities. Now one can use standard tooling to also handle that. All right, so now we covered how configurable we could be, right? How customizable, but how good in terms of performance can we get? Well, this is a key element of OpenFPGA. OpenFPGA enables you to use optimized standard cell libraries. The cell library has a strong impact on the FPGA matrix because 90% of an FPGA is based on is made of configuration chain flip-flops and multiplexers. So if you are using flip-flops, DFFs, as well as if you're using, fully terminated input and output terminated multiplexers, you're going to lose a lot of area and performance. What you want to do is to be able to craft your architecture in such a way that you make the most used blocks very compact. Here's an example, for example, where we created for a 40 nanometer tech node a T-gate-based MUX2 cell that is 2.5 times smaller than the one from the standard cell library, as well as a configuration chain flip-flop that is about 1.8x smaller than a regular DFF. This is a key element to enable compactness of your layout. What I'm showing here is a graph showing the array evaluation at the 40 nanometer technology node for Stratix 4, so Intel PSG Stratix 4 resembling architecture of a CLB. I'll pass on the previous work, right? But OpenFPGA already improves a little bit some of the previous work. It's essentially the way we generate our multiplexers, the way we keep things tighter, right, in physical design. But what is the key element here is that one can really use those custom cells to significantly reduce the area of your blocks, bringing you a relatively close-in gap compared to a full custom commercial FPGA layout. This can be further bridged, pushing the scripts, pushing the cells. We are currently looking into that, but that's to give you some perspective that, adding a few custom cells already have a very large impact, and that the fabrics generated by OpenFPGA are already of high performance, or I would say are cost efficient relative to a commercial full custom FPGA. Remember that this kind of layout is generated in 1 day compared to 1 year of many engineers to fine-tune all the layouts. Performance-wise, it is also quite interesting. What we're showing here is the performance of the different silicon elements compared to previous work, as well as commercial products served as a reference right here. We are considering their slow, and typical corners. It is hard to tell which corners are used in the context of a Stratix 4 or like any commercial product, as a matter of fact, because it's all a question of speed binning and taking the margins. Typically happening in the ASIC world is probably not the most relevant. Anyway, what can be said is that using our system, one can create a fabric that has nothing to be shy of commercial products. So timing-wise, we end up being fairly close to what full custom layout can produce. All right. So from there, I'd like to generally conclude about the OpenFPGA project and briefly look into the future. So OpenFPGA, hopefully you've been able to assess that by yourself. It's one of the leading open source FPGA IP generators. It supports highly customizable architectures. It has one of the most complete open source EDA support, and it enables high performance fabric generation and 24-hour development cycles to look and evaluate new FPGA architectures all the way down to GDS. In order to promote that effort, and as a result of starting to see significant traction around the project and FPGAs at large, myself, as well as a few industry veterans, such as Navid Chawani, former CEO of Sci5 and current CEO of Rapid Silicon, Brian Face, from the CEO of QuickLogic, Von Beth from the University of Toronto, Serge Leaf from DARPA, Nani Demicheli from EPFL, we all got together and founded the Open Source FPGA Foundation. The goal of the Open Source FPGA Foundation is to democratize FPGA technologies to provide open, user-focused, and collaborative environments. And OpenFPGA is now a project under the Open Source Foundation. So you'll tell me actually why, opening a foundation? Well, because I'm a strong believer that technology alone does not guarantee adoption. In fact, what you need to do is to create an ecosystem around that, an ecosystem where, and I highlight just a few couple of items, governance is a key aspect, right? We should not be in closed circles. We need to be able to account for requirements that are the most meaningful to other users across the world, as well as industrial partners. Education and training is one of the fundamental aspects. We want to be able to provide training material, training opportunities, and educational opportunities all over the world for people interested in FPGA technologies and chip design. I'd like to highlight on that front that OpenFPGA initiated the Tape-Out World process, for which whose goal is to actually partner with local institutions in various countries and create tape-out opportunities for students. It's been extremely successful so far in Pakistan, Turkey. It is growing in many other areas as well, and we have chapters growing on that front. Please reach out to me, Shal, you are interested about that. But again, so technology alone is not does not guarantee adoption. You need to have all of that to support that, and this is what a healthy ecosystem will do. A healthy ecosystem will guarantee adoption, and I'm actually very happy to mention that a week ago or so, QuickLogic Corp actually announced the Australis eFPGA IP generator, which is their own proprietary version or their own solution to provide eFPGA IPs that is fully built upon OpenFPGA. So QuickLogic took OpenFPGA. We worked with them for months and years in adding new features, adding new support that is part of the open source, but adding their own domain expertise and past expertise in designing complete IPs and productizing IPs. They have been able to create a product around OpenFPGA. So with that, I'll stop my presentation for today, and I'll be extremely happy to take any additional questions you might have. Thank you.
Let's see. Okay, thanks a lot, Pierre, for this nice and interesting talk. Let me see if I have questions. I have not questions for the moment, but I have someone. I have a question, for example, an important feature recorded in industrial designs are multiple clock domains. You take, for example, Xilinx or, let's say, Intel Altera, they have PLLs, DCM, and so on and so forth. You mentioned that OpenFPGA can support multiple clock domains. Which are the limitations and how you manage this queue, for example, when you have multiple clock domains?
Yes, absolutely. So multi-clock domain is actually is actually a complicated problem, right?
I know.
Because it is a problem that spans the hardware support, right? You need to have multi-clock trees. You need to have ways to select multiple clock sources to your flip-flops, all that kind of things, right? It is, again, very different from ASICs, where you know what your clock domains are. You need, in the hardware of FPGA, you need to be able to support everything, right? You need to be able to support the implementation of multi-clock domains in a programmable way. That's one part. The second part will be about the end user tooling, right? And supporting, synthesis across multiple clock domains, supporting STA across multiple clock domains, all that kind of stuff. What OpenFPGA does support mostly right now is the hardware part. So we're capable of handling multi-clock trees. We're capable of stitching things to multiple PLLs. We're capable of having all the programmable clock routing, not at the level of what a modern fabric such as Xilinx and Altera do, which is having really programmable clock routes. We have fixed clock trees and selection that can be done at the input of your logic blocks. We do not support those notions of useful skew, for example, for not supporting retiming, that kind of things, right? So there are some hardware limitations for sure, but already OpenFPGA supports multi-clock trees, PLL stitching, and programmable selection of multi-clock sources to the flip-flops. Software-wise, there is still quite a few things that needs to be done. Right now, it is essentially up to the user to create, the RTL the proper way with their multi-clocks, and then you feed that into the system. We place it to respect that, but that's what we have. Does that?
Can you have different regions of the system work at different frequencies, for example?
That's right. You can make that. You can make the granularity at different regions, like quadrants, for example, or also per column or per CLB basis. So you just, you can think, for example, of a big FPGA separated in 4 quadrants. Each quadrant had its own clock trees, actually. And then within the clock trees, you can select which clock tree feeds into which CLB. So there's a lot of versatility, but once again, the OpenFPGA framework is about generating the architecture you fancy the most for your application, right? Or for your application domain, right? So it is work in progress. We keep adding new features. There you go.
Okay. Well, I have a second question. You showed that you have integration, for example, with RISC-V.
Yep.
Software, and also you can make partial reconfiguration in your system. So there is a way or some API, for example, to run software and on demand change a given accelerator and reconfigure the system for a given accelerator. For example, let's say I need an accelerator for convolution in machine learning. It's possible to make in software the selection of a given region of the FPGA and reconfigure it.
Absolutely. So I did not provide any slide material for that. I actually removed this slide 30 minutes before the talk, which probably was not a good move. But we do support indeed multiple, we call them programming heads. So like, instead of having a single scan chain, you can have multiple scan chains, so multiple independent regions for programming.
Yes.
So we do support that. That gives you the ability to indeed reconfigure your system, right? We have, as you noted, RISC-V and eFPGA SoCs. What we have not built yet would be the top-level software support on top of it, right? Because you need, if you want to support ideally, accelerators, you need to, OpenCL kernels, and how do you map things, and it adds a level of software complexity that is not part of our ecosystem, but we would love to see being developed or contribute to.
Let's see, we have some question. We have here a question from Ricardo Reis. How difficult it is to adapt OpenFPGA to different types of FPGAs?
So I assume Ricardo's question is about adapting to, like a small 4-input LUT FPGA to a complex 6-input LUT FPGA and or adjusting to a given tech node. That's actually the beauty of OpenFPGA. It is very simple to do that. So to give you numbers, right, adapting from a tech node to another is about it's a week type of process to bind all the standard cells, knowing what to do. And it is about, 3 weeks to adjust physical design scripts and methodologies. So a month to adapt to a completely new process node. For adapting to different FPGA types, so first of all, we maintain 100+ FPGA architectures in our repos. So there's, all of them working and fully tested. You can just pick up the one you prefer and move with that. But making a modification to the FPGA architecture, changing the architecture, changing the number of LUTs, all that kind of things, it's typically a day type of process, right? It's modifying things, debugging to make sure that you have not messed up with the syntax, right? The syntax works correctly and it does not make anything crash. And from there, push a button and you can get the complete GDS with your actual performance, area and all the PPA numbers at the end of the day. Okay, so it is very easy to move from a tech node and an FPGA type to another.
And my last question here, is what do you think to have a specialized architecture, for example, for machine learning, to accelerate, for example, convolutions or some neural network, deep neural network?
This is an excellent question. This is actually an excellent question. So let me start with some facts, right? So FPGAs are extremely popular right now to accelerate machine learning, not only because you can implement custom hardware, but because they distribute DSP and RAM.
Right, exactly.
Right? So it's really a highly distributed architecture. Now, if you look at actually some statistics, most of neural network implementations today on FPGA max out the number of DSPs and RAM blocks. So the scarce resource is not the logic, it is the number of VRAMs and the number of DSPs. With an infrastructure like OpenFPGA, you can craft a domain-specific fabric that will contain more DSPs, more RAM blocks, that will group them close together in order to have some sort of in-memory computing type of things. Exactly. So you can really work with your weights nearby and that kind of stuff, right? So you can, AI is a perfect example actually on why domain-specific FPGAs do have a future, because you can actually just tailor that for your problems, class of problems. So yeah, to answer your question, the simplest way, the simplest exploration that can be made is just, okay, you take OpenFPGA, you increase by 3 times the number of DSP and RAM blocks compared to number of LUTs. So you change the ratio between them, and that will already give you a big performance boost for AI.
Yes, it's a good path to follow.
Exactly. And then one can imagine to, start customizing your LUTs, customizing your DSPs, adding eventually more hard IPs and hard macros to handle, sigmoid functions or whatever that is, right? You could imagine to create specialized blocks inside of your fabric for specific applications that are important to you.
Okay, thank you very much, Pierre, for your talk. Nice talk. Now, Ricardo is there.
Thank you very much.
Yeah.
You're welcome.
So thank you very much, Pierre-Emmanuel, for this very nice talk in a very exciting subject, and congratulations for your work related to FPGA. Thank you also, Fernando Moraes, for chairing the session. So I will now remember you about the next activities. So next week, before that, the ones that accepted our invitation to include their name and where they are now during the talk of Pierre-Emmanuel. So we were able to see that today we had people from Spain, Germany, Costa Rica, Uruguay, different locations in USA, France, and for sure different locations in Brazil. But next week, it's a very special week. So 2 years ago, we had the second edition of the seasonal school on sequencing system for IoT here in Brazil from Porto Alegre. It was a face-to-face one. And then now we have the third edition next week from Bordeaux. As you can see, it's an hybrid mode. And Francois Rivet, that is the general chair of the seasonal school, is attending this session today. So thank you, Francois, and thank you for organizing a very nice program also with all the program chairs and the general chairs of the seasonal school. So this will start next Monday. So the virtual mode registration is free. This is still open. So I recommend you to go to the web page to see the very nice program going from circuits, analog communications to computing issues like machine learning, deep learning. And so it's a very, very nice program. So don't lose this opportunity to attend a very nice seasonal school that is completely free for the virtual participants. There will be also a nice number of participants that will attend the school in person in Bordeaux. So that's the reason that next week we don't have a CASS talk, because we have a large set of nice talks during the seasonal school. Then the week after, we have still to update here the list of confirmed speaker. So we have also more people than are listed here, but you can already see that we have Abby Friedman from University of Rochester in USA, Arjuna Mandanayaka from University of Florida, Hilsam Amaroch from University of Stuttgart, Helmut Grab from Technical University of Munich, Jimmy Tarillo, Universidade de Engenharia e Tecnologia in Peru, Jorge Castro Godinez from Technology in Costa Rica, George Tonfra from the Space Research Institute in Graz in Austria, Felipe Rosa from ARM in UK, Yu Bufan from Fudan University in China, Gustavo Vilke from Google USA, Graciele Posser from Cadence, Texas, USA, Guilherme Flack from Synopsys in USA, Arthur Linaetro from former HT Micro in Brazil, and many others that will give a nice. You go to the web page, you can see the full program, and so it's also, the registration is also free. That's also with all this set of nice talks. We are not going to have a specific CASS talk the week in October 1st, but in October 13, 14 also, there is the Think Lab from ground up to cloud, that is the 4 AI Compute Symposium sponsored by IBM and IEEE Security Systems Society and the Electro Device Society. The registration is free. You can see the program by attending the web page of the event. And then also it's open till next Monday, the registration for Nano Connected 2021, that will be generated from Montpellier, so it will be a hybrid event. And the free registration, as I told you, is open till next Monday. And going to the web page, you can see that each day is dedicated to some of the fields related to nano technology. On Monday, especially, we have nano electronics, and you are all invited to participate. Then also we have next Monday the extended deadline of the call for poster for the 5th seasonal school on digital processing of visual signals and applications, that will be organized from October 26 to 29. And then on October 8, we have the next CASS talk with Professor David Atienza from EPFL Switzerland, talk a brain-inspired edge AI architectures. And you have in this YouTube channel the list of other talks that are scheduled till next November. So thank you again, all you that attended this session today. And thank you again, Pierre-Emmanuel and Fernando Moraes, for the talk, and also for chairing the session today. And I wish a very nice weekend to all you, and see you next week in the seasonal school on Secrets and Systems for IoT that will be transmitted from Bordeaux, France. Bye-bye.
Bye-bye. Thank you.